Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, well, thank you very much, everybody, for coming. I'm really excited to have Benjamin Brown here from the University of Copenhagen, who will be talking about fault-tolerant quantum technology. Thanks a lot, Ben.
Thanks. Yeah, thanks for having me. Okay, so the title here isn't what I wrote in my abstract. Actually, I got a little confused because Krista told me 50-minute research talk with a little bit of extra stuff, and a couple of days before I came here, I had somebody from Matt from recruitment. He told me, no, it's an hour and a half, and you should spend 20 minutes talking about your background a little bit as well. And so this was told to me the night before the morning I flew. So yeah, there's now about 20 more minutes of slides at the beginning, 20-ish. I haven't rehearsed it, but I guess 20 minutes on my background. Yeah, I did it on the plane very apologetically. But if I look surprised about which of my slides come up, it's because I am.
Many of the best talks are carried out that way.
Yes. Okay, so this is a little bit of PowerPoint karaoke. Okay, so yeah, so I did most of my research so far has been done in my PhD, and pretty much an overlying theme has been topologically ordered phases of matter and their applications, specifically their applications to fault-tolerant quantum computing, hence the title of the first part of my talk, fault-tolerant quantum technologies. Okay, so the 20-minute part, I'm going to rush you through things that I've done so you know all about me, recruitment asked. So this is going to be a little intro to what topological phases are and anyons. And some work that I've done has been studying topological phases with entanglement entropy, applications of topological phases to quantum error correction. So I'm going to talk a little bit about quantum error correcting codes. Okay. I've done some work with some experimentalists on what I would call quite a novel way of preparing quantum error correcting codes, not topological ones just yet, but we're thinking about it. And finally, I'm going to tell you a little bit about self-correcting quantum memories, and these things pretty much summarize my research background. And then finally, the talk that I had prepared for, I'm going to put a new title slide when I get to that, and this is the regular scheduled program, the research talk on error correction with the gauge color code. Okay, so I'll start. So right, topological phases are very interesting, just from a point of view of fundamental condensed matter physics. Lots of work has been done here and with other people. I guess the pioneers of this field are Zhaogang Wen, Alexei Kitaev, and Michael Friedman, who's also at Microsoft. Matt Hastings has done lots of work too. Right, so these are physically realistic systems. We consider locally interacting systems of spins. And what's particularly interesting is we take this system and we put it on some manifold of varying genus. So here's a manifold. It's a double donut. It's got genus 2 because it has 2 handles. And what's interesting about topological phases is they have degrees of freedom in their ground space that can only be accessed via non-local measurements or non-local operations. So right, and those non-local operations are supported on non-trivial cycles of the model. So yeah, this is exactly the picture I have in mind. We have some non-trivial manifold, which is this big blue shape. Thought 2 handles would make it look more exciting. It interacts locally, so the Hamiltonian terms involve spins that are very close together. And right, we have non-local degrees of freedom that are accessed via measuring the handles of this model. Right, and what's really exciting about these are they're stable under weak local perturbations. So that means even if the Hamiltonian isn't perfect, if the perturbations are small and local, we still have the same physics. This is, again, some work by Matt Hastings and some others who's obviously here. And what's really interesting for me is the low energy excitations of these Hamiltonians are anyons, or generalizations thereof. So these are pretty interesting just fundamentally as particles. They have braid statistics whereby, OK, so here's a picture of that manifold. And let's suppose I excited some particles, and then I start moving them around. What happens is, as I braid these particles, I acquire non-trivial braid statistics, which I can use for all manner of things, quantum error correcting codes or topological quantum computation, which, yeah, is another big subject here, right? OK, so, right, and this is, yeah, these are interesting fundamentally, and these are interesting for their applications to fault-tolerant quantum computation. And I'm going to talk a bit about both of those things. So, OK, so some work I've done is concern the study of these topological phases fundamentally. So one way we can study these models is by looking at the ground states of these Hamiltonians, and we look at the entanglement of their ground states. So we take a lattice, or so you can imagine, say, this square as being that some non-trivial manifold again, where maybe the sides have periodic boundary conditions. We have a torus. OK, and we take the entropy. So we take all the qubits inside a region and trace out the qubits outside. And we look at the entropy of this, of a pure ground state. And it turns out, by results due to Kitaev and Preskill and Levin and Wen in 2006, that we can learn a lot about the topological characteristics of this model. So specifically, we would expect the entropy to typically scale like an area law. So there'd be some constant term times by the length of the boundary. So LR is the length of this red line separating part R from its complement. And if we have some topological phase which supports anyons as its low energy excitations, we also expect to see this universal term. So this term gamma tells us some property of these phases of matter. OK, and we can learn about these, right, so a small extension of this result is we can take many entropy calculations and take linear combinations of them, and we can isolate this gamma term. And this is what we call topological entanglement entropy. OK. Right, so I've studied some topological phases in this respect. So something I think people here are familiar with. Alan Geller and Matt Hastings have a paper on distillation codes. So what I've studied is if we take some topological phase, so namely the turret code model, which I'm going to talk about later, it supports two types of anyons that have mutually non-trivial braid statistics. One type of excitation lives on the blue squares of this chessboard, and the other type of excitation lives on the green squares. And we can introduce dislocations to this code. So you can see what I've done in the middle here is I've taken the squares of the chessboard and just shifted them. And this reverses the coloring. So the coloring of the chessboard is, I can no longer globally color this in a way that's globally consistent. And what's really interesting about these guys, which we call twists or twist defects, or maybe dislocations, is that these, in some sense, non-trivially change the topology of the system. So you can kind of regard taking this chessboard and introducing twists as introducing wormholes between the green slices and the blue slices. And in this sense, you can see that I've added more handles to the shed between the blue pieces and the green pieces. And in fact, so these twist dislocations, it's been shown by Hector Bombin, they behave a lot like Ising anyons, which are kind of like Majorana modes, if you prefer that terminology. Right. So some work that I've done is to study these twist defects on the lattice. And I would take the entropy of these regions and various topological entanglement entropy configurations. And what we've seen is that these twist defects that look a lot like Ising anyons in many respects behave like Ising anyons also with regard to twist defects. With regard to entropy calculations. And we did various diagnostics on these. So here's a bunch of calculations we made. So the topological entanglement entropy should depend on the twists that live inside this region, this D1. And yeah, so we did all of these tests. So in the case that we have one twist in this annulus, we observe an Ising anyon. And then if we put 2 twists in this, inside this annulus, it behaves a lot like, well, it now depends on the internal state of the fusion space of these Mayer anomodes or Ising anyons. And it turns out that with this analogy, the analogy still holds with respect to entanglement entropy. And a little further work I've done. So topological phases are even more interesting, it turns out, in 3 dimensions. And we don't have a very good way of characterizing these guys yet. So in 3 dimensions, as well as having point-like anionic excitations, we also have these loop-like excitations where, so these are the excitations of the 3D toric code. And point excitations dragged through loops will give you non-trivial braid statistics, as illustrated here. And it turns out, and we also have models that are topological in some sense, but don't have a good topological entanglement entropy if we just look at the bulk. So some other work I've done regarding the topological phases is to study the boundaries of these types of models. And together with Isaac Kim, we came up with 2 different types of diagnostics where we look closely at the boundary, and we take the entropy of regions close to the boundary, and we can find boundaries that support different types of point excitations, and also boundaries that support different types of loop excitations. And this is really interesting because we can't tell these things apart by our entropy calculations in the bulk of the system. We have to go to the boundaries. This is all kind of cool, I think. OK, so this is all my work on topological phases. I'm now going to talk more about practical stuff. So the reason why we think about topological codes or topological models as being good quantum error correcting codes is because we encode information non-locally. And typically, a big assumption we make in quantum error correction is that a noise model will only act locally on the physical spins or qubits of the system. So what this means is the noise model has to be either very fierce or it's got to conspire in a bad way before the small local errors will start to affect the non-locally encoded information. And so it turns out that topological codes, as far as I can tell, are some of the best candidates of quantum error correcting codes we have at the moment. And so quite a lot of work I've done has been concerning different types of codes. I don't want to talk about this too much because the gauge color code is going to be the main topic later on. But yeah, so certainly it's interesting to figure out different ways of identifying the errors that have been introduced to these topological codes, and different ways of different classical algorithms we can use to try and determine what error caused some configuration of syndromes or anions, as I was talking about them earlier. So I've done some work with some guys at UCL and Earl, who's now at Sheffield, comparing different decoders for toric codes of varying spin dimension or qubit dimension. And I've also done some work with the gauge color code. Again, I'll talk about this later. OK, so this is all very interesting. But what we do really need to think about is how are we ever going to build a quantum error correcting code? Maybe not even a topological one, just any kind of quantum error correcting code. And people are starting to get quite good at it. And I guess that's why lots of people are getting excited about quantum computing recently. So of course, we all know about what's going on in Google in the Martinez group. So these guys are now capable of making a very small classical error correcting code, which will detect bit flip errors. And they can measure syndromes to identify these errors. So syndromes are measurements we make to spot where the errors are and try and figure out what the error is. OK, and these guys are on the way to trying to build some toric code, but hurdles still remain as far as I can understand, to the best of my knowledge.
Do you have a sense if they can do many rounds of error correction?
My understanding is they have done some number of rounds. A talk I saw by Martinez led me to believe that that's what they've done. Yeah, OK, and so people also consider ion trap quantum error correcting code. So a small 2D color code has been performed by the Black group in this paper. So the smallest color code is the Steam code. And this is interesting because it will perform the whole Clifford group fault-tolerantly. OK, but maybe this isn't the best approach. Right, so another way we might think to put all of our spins together is using the distributed picture. So I spend quite a lot of time. So Naomi is a co-author of mine on the gauge color code paper that I'm going to talk about later. But what these guys think a lot about is, well, OK, maybe it is really hard to put a lot of qubits together. So maybe we just manage to put a few together. Like an ion trap, we can control 7, 10, 15 ions really, really well. but 15 ions isn't going to make an arbitrarily sized quantum computer. So maybe, though, if we can take these really well-controlled qubits and connect them via fiber optics or some channel of communication, then perhaps we can build a quantum computer over many, many ion traps. So this is what's called the distributed picture. We have small islands of a few qubits, and they're all linked via fiber optics. So this is also a research program of Chris Monroe and some others, I believe, who I can't name. Oh, so these images are courtesy of Simon Benjamin. Carl Nyman is the graphic designer who made this cool torus. OK, right. So I've spent a little bit of time thinking about how we can realize quantum error correcting codes in what's called a penning trap. So a penning trap is kind of interesting. So maybe you're familiar with the work of the Bollinger Group from about 3 years ago. So they showed, there they simulated in a penning trap. So a penning trap, just to be clear, it's some electric field that combines a bunch of ions. So these are charged particles. And to keep these particles stable, the trap has to spin round and round and round and round and round. Otherwise, yeah, the ions will go missing. OK, and what they can put like between 100 and 300 ions in this trap, which is quite a lot of ions compared to what Blatt is doing in what's called a pull trap. But the only trouble is, because these ions are spinning around so fast, the operations you can perform on them are quite limited. You can't address single ions, for instance. Instead, what you have to do is you shine a laser at the whole crystal, and whatever happens, happens. OK, so so I should talk a little bit about my background at this stage. So I was very lucky to go to the Control Quantum Dynamics graduate school in Imperial College. And so they're trying to make, just to be clear, in the UK, they're trying to make PhDs a bit more like the US system. And so this particular graduate school, we were put in a class with a whole bunch of people wanting to do quantum stuff as their PhD. And we all did a master's together. We make friends. And in the end, when we kind of start to learn how to do quantum mechanics, we start talking to each other again. And so I was talking to this guy, Joe Goodwin, who was in my class. And he worked in the penning trap lab at Imperial. And he said, OK, what can we do with this? I think we can do operations that are rotationally symmetric. We have this crystal, and it's spinning around and around. The crystal is rotationally symmetric. What can we do? And I say, well, the 5-qubit code, that's rotationally symmetric. Right, so now what we're going to try and do is build quantum error correcting codes inside this penning trap. And this is kind of a cool idea, because we have so many ions in there compared to a pull trap. Right, so like I say, so here's a penning trap. Ions are confined in this 2D crystal, and they're spinning around and around and around. Qubits are encoded in the spin degrees of freedom. And we use these cross lasers to access, to couple to the spin degrees of freedom. And we can apply. What does it mean, D2? It means the frequencies are slightly different. So you get like a beat pattern where these two lasers cross. Yeah. They're just slightly off resonant. Yeah, so in actual fact, this is the really nice thing about this grad school, because I don't know these things either very well. I count on the guys working on ion traps to answer these questions to me as well.
Can you explain again why the symmetry of the trap is reflected by the symmetry of the code? What's the connection there? Really?
No. It's not like we want this code, so let's make the trap this symmetry. The question really was like, look, the ions are going to have this symmetry. What can we make with this? And I just started showing out the codes that have this symmetry. And so the 5-qubit code turned out to be fine.
But wouldn't it be the same as saying, like in a Paul trap, that you have a symmetry of the chain?
Well, I would say it's probably not quite long enough to start imposing translational symmetry. I mean, 10 isn't so big. And again, it is only like 10 or probably no more than 20 for sure.
Get individual addressing. He's got to address everybody here globally.
That's right.
So this thing's spinning around. You can do the same thing to all 5 all the time. That's
the part I was curious.
Right. Yeah, exactly. So exactly. This is the picture, right? So these purple arrows, these are laser beams, and they're just shooting at the crystal.
So very restricted
Yeah.
And
So
with the detuning, he gets to flip the spin however much he wants. And so that's his way, for amount of time, I assume you
That's
shine
right,
a
that's
laser.
right.
That's how much rotation you're going to get on all 5. So the question is, what can you do if you do all 5 at once?
exactly. So okay, we do allow ourselves a little bit in this particular instance. So I'm going to describe in my next slide a whole protocol. But we do allow ourselves some single qubit addressing of this middle guy. So the hub guy, so all this ions spin around it, and the central guy is static. So we're gonna we can get to him. Yeah. Okay. So right, we can do this entire protocol. And what's amazing is with these global operations, we can do it really fast as well. So we can. Right, so we start in this configuration. We suppose that we can rotate this central. Okay, so in all these pictures, the blue ion is, that's where, the blue ions are where the information is. So we assume a product state where we have a qubit on a logical qubit that's on one physical qubit, and we want to teleport it onto the code that's going to be on the outside ring. Right, so we have global operations that entangle this central guy to the code. We measure to teleport the information onto the code. Okay, in actual fact, we have two different codes we can prepare. The first one is the 5-qubit repetition code, which is just a classical code. But so far as ions are concerned, this is kind of interesting because the code that we make is the repetition code that defends against dephasing errors. And since dephasing errors occur much more quickly than the bit flip errors in the ion trap, it's worth doing this and very easy. Right, so if we want to, after we've teleported onto the 5-qubit repetition code, we're then able to rotate the repetition code onto the 5-qubit code and defend against an entire quantum set of noise. Like any one of those ions can suffer a bit flip or a phase flip or a combination of both, a Y error. So we leave it, and then we can re-entangle the code onto the hub qubit, and then we teleport by measuring the outside qubit. So this is done by fluorescence. We just shine a laser, we excite. We shine a laser at all of the ions and we make them fluoresce. And it turns out not only when we fluoresce and teleport the information back to the hub do we recover the information, but we also learn syndrome information. So there'll be some fluorescence pattern here that will tell us what correction we need to perform based on what errors have occurred when the information was on the code. And what's really great about this is so even the 5-qubit code operation, we can do this entire procedure in just 10 pulses, like zap, 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 and the information is in and out with syndrome information as well. And if we want to do the repetition code, which is also worthwhile, we need only 6 pulses. And to compare this to what I talked about before, the ion trap of the NIG paper with the black group. So if they want to actually read syndromes, it takes them hundreds of pulses of single qubit addressing. And all we had to do was figure out what types of unitary operations we could perform by shooting lasers at the whole crystal all in one go. So this is actually ongoing work. We've published this result with small codes, and we were actually criticized by our referees for not making this scalable. We were limited. So the way we found these was just numerical searching. We knew all the global operations we could perform. We knew what unitaries we wanted to do to get through this whole procedure, and we searched for them.
What sort of T1 or T2 times instead E do you get?
So the numbers, I think the dephasing occurs about 1,000 times quicker than bit flips. Between 1,000, 5,000-ish, these are the numbers. Ions don't flip very fast.
And how long is the dephasing time?
That's a good question. We did. I trusted my ion trapping guys on this. Everything was done in unitless ratios of coherence times. I could tell you after the talk if you like.
Is it obvious that 5 is the best number?
5? No. So it's not. We want to get to really, really big codes if we can. So after we did this work, I'm going to tell you about this now. We want to be able to make codes of arbitrary size if we ever want to make an arbitrary size quantum computer. So we had a master's student work on this, in fact, and he's figured out how to make a repetition code of size n in this penning trap. And we figured out, we think we're still working on this, but it seems worthwhile with the dephasing, the T1 on T2 times I just mentioned, to actually think about building a code of size 20, 50-ish before bit flips actually become appreciable.
Is it conceivable at all of this kind of an architecture that you could ever go to 2 qubits?
Yeah, that's an open question that I put on my last bottom point. Okay, right. So okay, there was another issue with what I showed you before. So again, because single qubit addressing was difficult, syndrome readout was tough, and we could only do it when we wanted to read the information out of the code. So not only can we now produce, we can take a crystal, a big circular crystal, and put a really large repetition code on here. So this was done much more analytically. We did it brute force numerical searching, but this guy, he's called Yannick Says. This paper will be out, I hope, in a month or two. He just looked at one global operation, and it turned out we could do a lot of stuff with the repetition code. But not only can he produce one really big repetition code, we can also take the crystal, partition it into 2 pieces, and separate it into 2 separate codes. And in actual fact, we can entangle these 2 codes. And every time we teleport, we learn syndrome information. So, so we can perform repeated syndrome readouts by teleporting the information from code A to code B to code A to code B. And so this is allowing us to learn lots of syndrome information. So this is making for a really cool code, actually. As I say, we're now limited because it's only a classical code. It would be nice to explore a few more of the global operations we're allowed to perform, and try and find some quantum codes that we can make arbitrarily big in this. I have a couple of ideas on how this might work, but let's see. I think this is already a cool experiment for somebody to try, and totally feasible in the Bollinger lab where they're doing these simulations already, I think. I hope it is. Maybe somebody will tell me why not. Right, and yeah, so your question, like, can we put more qubits in this? So maybe. So maybe we can take this crystal and partition it into a few more pieces, and then maybe put a few more logical qubits in one crystal. Or maybe we can combine this idea with the idea of the distributed picture I showed you before. So another question might be, well, so the way we work at the moment is we put an arbitrary qubit on the hub, and then we teleport it onto the code. Maybe if we can get some optical access to this guy, maybe we can start entangling this to another code of a similar. But I don't know how to do that. That's something. These are 2 questions that will make this actually a pretty interesting way to encode qubits in a distributed picture. Okay. So then, finally, to summarize, one other part of work I've done, I've worked on self-correcting quantum memories. So this is a pretty interesting. So what this is all about is how do you build a quantum hard disk? So the reason at the moment, the reason you can think of why our computer can store information for a really long time is because we have a hard disk. And so a few years ago even, we could have thought that this is a big piece of ferromagnet. And provided the temperature of this ferromagnet stays small enough, information can be encoded in the ground space of this ferromagnet, where either all the spins point down or all the spins point up. These correspond to a magnetic dipole. And the reason this was robust against thermal errors, like just the fact that this piece of magnet is stood there at room temperature, is because every time the environment tries to put some energy into this system, the energetics are such that there's a very large energy barrier trying to separate 2 ground states. So every time the environment tries to put energy in, the system just wants to spit it back out again. And so the errors remain very small and don't really affect the encoded information. And we can always fix it at the end. Ultimately, it's the physics that's protecting it, right? So collectively, this Avogadro's number of atoms is producing a field that points in some direction, and every time one atom gets a little bit of energy to try and flip against the global magnetic field, the magnetic field will try and pull it back into line again. And this is where you can think of the Ising model as being a good model for a classical self-correcting quantum memory. And the question is, can we emulate this in quantum physics? Turns out a quantum hard disk is a really hard problem, and it's even not clear. We're not even asking, can we build one? The question is even, like, can such a thing fundamentally exist? And we need to know a lot more about Hamiltonians before we can say such a thing. So one model we know we have is the 4-dimensional toric code. So that's why I have a picture of, so this is a building in Paris called the Grand Arche de la Défense. And so the architecture of this building, so if you want to draw a cube on a piece of paper, you can draw a square inside a square and connect its vertices. So this is the architecture of this is a 4D hypercube or a tesseract. So it's a cube inside a cube, and the vertices are connected. So the architecture of this building is supposed to look like a 4D hypercube. If you learn nothing else from this talk, you've learned something about some architecture. OK, so I did some work on this. I've written a review article, in fact. And there's all kinds of interesting models, and none of them really work very well. So probably my favorite is what's called the qubit code model, which was discovered by Zhongwon Ha and studied by Zhongwon and Sergei Bravi. And so this model is partially self-correcting. So so what we want to do is we want to take some model, we want to make it arbitrarily big, and we expect qubits to live in the ground space of this model for an arbitrarily long time. So this code looks a bit like a self-correcting quantum memory. The memory time will grow for a short while, but if the model gets too big, the energetic protection that we have in the, for example, the 2D Ising model, it falls off and it doesn't work anymore. So people have also considered non-commuting models, so subsystem codes. Maybe the most famous example is the Bacon-Shaw code. So there are good arguments for why this might be a self-correcting quantum memory. There are lots of reasons why it won't work. But ultimately, because it's a non-commuting Hamiltonian, we've not really got a good way to solve it. So yeah, this is an interesting way to explore. So,
at a high level, describe these difficulties. I remember that in the 2D case, there was no gap, right?
Yeah, so
But
this is probably gap.
What happens in the high Z?
Maths isn't good enough. Just like we can't diagonalize these Hamiltonians to say anything useful about them. So like David Bacon's argument for why this should be a self-correcting quantum memory is based on Mean field theory. And yeah.
Is there numerical evidence that it might be a self-correcting?
As far as I know, nobody's even simulated this numerically. Again, because it's a non-commuting Hamiltonian, it's really intractable. Well, non-commuting and three-dimensional. So like the third biggest system, well, supposing one qubit is the smallest system, you then need 8 qubits, and then you need 3 by 3 by, there's 27 qubits, and like this is getting kind of tough on a classical computer to analyze, I think, given you need.
Did anybody seriously try?
Somebody told me a little while ago that some people were working on this, but I haven't seen that paper. Yeah. In any case, this is a hard problem, and but I would like to skip on to the talk that I was going to give. But yeah, this is a summary of the stuff I've worked on in the past little while. Right, so I want to tell you about the gauge color code and single-shot error correction with the gauge color code. This is a really exciting topic for me. So just to give you some background, lots of people think about using the toric code for a quantum error correcting code to realize universal quantum computing. They think this because it's pretty easy to build. The measurements we need to make to identify errors are reasonably straightforward compared to all the other codes I can think of. We can make it universal, adding magic state distillation. It's two-dimensional, so we can build it on an optical bench quite easily. This is still the problem Martinez is having, as I understand it. Right, but it's still fairly reasonable to try and think of magic state distillation is difficult. It's worth thinking of other codes to do this with. And also, there are other interesting ways of performing error correction, and I'm going to talk about that today, which is single-shot error correction. OK, so I am going to first talk about the toric code, and I'm going to talk about, right, so single-shot error correction. The error model we're imagining is all of our qubits are suffering errors, but also in a more realistic picture, when we try and make measurements to learn where these errors are, sometimes these measurements are unreliable as well. And this is, photons are lost all the time. You can imagine measurements being difficult in general. And I'm going to talk about different ways we deal with this problem of having bad measurements. And single-shot error correction is a pretty elegant way of dealing with this, I think. OK, but first I'll talk about the toric code just to explain where we are in this whole picture. So to talk about the toric code, we need the stabilizer formalism. I don't want to bore you too much with this. So we have a abelian subgroup of the Pauli group, and these form a stabilizer group. And we have code states of some quantum error correcting code, and they live in the +1 eigenspace of all the stabilizers of the stabilizer group. So S, a member of the stabilizer group, gives you the +1 eigenvalue of all the code words psi, and this is an arbitrary code word of the code I have in mind. OK, and Right, so Gottesman came up with this in his PhD thesis. Right, and so these stabilizers we also use as measurements to learn the positions of errors. So we suppose now not the code state, but an error times by the code state. An error acted on the code state. And by measuring the stabilizer terms, we find terms that don't commute with the error. And instead of getting a +1 eigenvalue, as we expect for the code words, we get a -1 eigenvalue. And we use these -1 measurement outcomes to identify the positions of errors. Yeah, so the reason, by the way, the reason we're allowed to restrict onto these Pauli type errors is because when we measure these stabilizers, we project onto something pretty close to a Pauli error times by the code state that was encoded. Right, so because all the eigenstates of the stabilizer operators are Pauli errors times by code words, we project onto a Pauli error. So this allows us to restrict to these types of errors. Okay, so the model we have in mind is the turret code. So again, this is a topological code like I talked about at the beginning. So this is a lattice of qubits. Qubits live on the edges of this square lattice. And the lattice has periodic boundary conditions and so lives on a torus, thus the name the turret code. Okay, and so Kitaev came up with this. Everybody knows that. And right, so it has two types of stabilizers: star operators, which are the tensor product of 4 Pauli X operators on all the qubits that are adjacent to a vertex, and plaquette operators that are the tensor product of Pauli Z operators on all the edges that bound a plaquette. So we have one of these for every vertex and one of these for every plaquette. And we can see quite clearly star operators will always commute with plaquette operators because either they have no common support, or if we take a vertex close to a plaquette, they'll have a common support of 2. So here we have a stabilizer group. Okay? And the logical operators, as I mentioned, with topological codes, they are supported on the non-contractible handles of this model. So here are the logical operators of a topological code. Right, so here's a string of Pauli Z operators that run around one handle of the torus. And this will anti-commute with a string of Pauli X operators that run along the opposite handle of this torus. And so you can see, so these logical operators anti-commute with one another, so we get the algebra, the logical algebra of a qubit. And the stabilizers commute with these logical operators too. And that's important because if we measure the stabilizers, we don't start collapsing logical information. Okay? And right, so how do errors look? So here's a Pauli error on the turret code, and we measure, right, so it's a string of Pauli X operators. Errors will look like strings, okay? So we measure all the plaquette operators on every single plaquette, and what we'll see is the plaquette operator, there will be 2 plaquette operators that don't commute with this string, and they will live at the endpoints of this string. You can see a plaquette that lives on the string will share 2 X errors with the plaquette, so that will commute. So what we'll see is a -1 outcome at the endpoints. So what we'll do to error correct this guy is we assume that the error model is relatively weak, so the number of errors will be quite small. And it should be quite obvious that if we apply some Pauli X operators that connect these endpoints again, that the syndromes will vanish. The -1 syndromes will be restored to the code space. They'll become +1 again. And you can see, okay, so suppose I apply Pauli X operators here to here. The product of the correction I made and the error itself will commute with both logical operators, and it will commute with all the stabilizers. So, we find the task of correcting the turret code is basically connect the dots, and we connect the dots with the smallest path possible. Okay, so we then imagine larger errors, and this is when error correction becomes difficult. So in this particular instance, here's a long string of Pauli Z operators. Once again, the star operators will identify 2 endpoints of this string. And now, because this string is wrapped halfway around the torus, it's now very difficult to error correct it. So if we start looking, so the only information we have are the endpoints of this string. And, well, the trouble is this correction operator that connects these 2 endpoints along this path, this will commute with both logical operators, but this correction operator is equally as likely to have occurred, as been caused by an error as this alternative dotted correction operator is. So you can see that if I were to apply this correction operator, the the correction operator will run across the support of the logical operator and cause a logical error by making this correction. So that's bad. And because the error is so large, there's no way I can tell one correction from the other. And yeah, so this would cause a logical error with very high probability. This error. Okay, right. So that's the prototypical topological quantum error correcting code. But what I also want to model is noisy measurements. So what I want to suppose is I measure some of those star or plaquette operators, and the measurement is wrong sometimes. So how do we deal with this? Well, in the case of the toric code, so this is talked about first of all in the Dennis paper, we measure stabilizers over and over and over again, and we try and identify errors as they occur. But equally, in some of these repetitions of the measurement, the error will go wrong. The measurement will go wrong. And so instead of measuring the studying the stabilizer outcomes themselves, we look at the parity between different times. So here's a one plaquette operator measured 3 times, one at time t minus 1, one at time t, and one at time t plus 1. And let's suppose the measurement at time t went wrong. So that's why I've colored in red, independent of whether these are identifying an error or not. Let's suppose there were no errors near these qubits. Well, because this has given me the wrong outcome, the parity between measurement t at time t minus 1 and time t will be -1. So we can effectively think of this as the endpoint of a string that runs vertically. And the other endpoint will appear when we look at the parity between the measurement outcome at time t plus 1 and time t. And so effectively what we have is a string of measurement errors that run vertically in time. Right, so the decoding problem now of the toric code. So here you can imagine a toric code living on the base. And we measure star and plaquette operators over and over and over again over many time slices. And now physical errors, they'll look like strings that run horizontally along horizontally in the plane of this 3-dimensional like space-time. Measurement errors will run vertically. And maybe we'll get some more complicated errors where a measurement error occurs at the same time as a physical error, in which case we have strings that run both horizontally and vertically. And yeah, so this is noisy measurements with the toric code. Okay, so here's a bunch of terminology now. We consider independent and identical noise models. This isn't realistic, most likely, but it's analytically and numerically tractable. Right, so the error model, we go to every single qubit and we flip a qubit with probability p. With probability 1 minus p, no error occurred on that qubit. Okay, so when we want to introduce measurement errors are flipped with probability q. I'm going to call it q, but q is always going to be equal to p. I'm just going to call it q because it's good to have another label for a measurement error. And when the probability that measurement gives me the wrong outcome with probability p equals q, we call this the phenomenological noise model, and this is the noise model we're going to work with. I'm going to talk a little bit about the gate error model. So in actual fact, the phenomenological noise model is a bit contrived as well, but it's interesting enough. It captures all the physics I'm interested in for now. Right, so the gate error model is where not only do we consider measurement errors, we consider the whole circuit that will conduct the measurement. So that involves having an ancilla qubit, coupling it to all of its nearby qubits that are involved in this parity measurement, and then we assume that every single gate I perform could have introduced errors to the system. And you can see then, with the weight of the measurement, the probability of error is going to increase. So this is an important error model to consider. People have done it for the toric code. I haven't got there yet with the gauge color code. Okay, so this is important to talk about. I'm not going to consider it, but I want you to know what it's called. Okay, right, and the first way we might consider studying a code is to study its threshold. So this is what we call a threshold plot. So this is actually a threshold I made for a different code altogether, but again, thresholds are very close to phase transitions. The physics is very similar. So on the x-axis, I have a plot p, which p is the physical error rate of all my qubits. And on the y-axis, I have the logical failure rate. So that's where I take some classical algorithm, which I call the decoding algorithm. I look at the -1 syndrome outcomes, and I try and predict what error caused that particular syndrome. And every time, if the algorithm gets it right, then that will be a logical success. And if the algorithm gets it wrong, it's a failure. So that's logical failure on the y-axis. So it's how successful my decoder is. And what I want is a threshold. So what I want is I want to show that there exists some error rate below which I can make the code arbitrarily large and get the logical error rate arbitrarily small. Right, so on this plot, I show a code of increasing size. And if I'm below threshold, which is at the crossing point, increasing the size of the code will make the logical error rate. OK, actually, so on this plot, this is the logical success rate. I got it upside down, I'm afraid. OK, so the logical success rate will improve with system size. At the crossing point, nothing will change. There's no sense in making my code bigger. And below that, it doesn't work anymore. But the interesting value is how much noise can that code actually tolerate, given a decoding algorithm. And if I have noise below that number, I can get my logical success rate arbitrarily large by making the code as big as I need. And then I can, in principle, get to a quantum computer of arbitrary, I can run quantum circuits of arbitrary depth because my qubits will fail that infrequently. My logical qubits will fail that infrequently. OK. Right, so the thing is, the final point I want to make about the toric code is the decoding problem becomes harder when we introduce measurement errors. So if we just assume bit flip errors and measurements are perfect, the toric code can actually tolerate nearly 11% of bit flip errors. And when we consider the phenomenological noise model and we decode in this 2+1 space-time picture, the threshold error rate will drop to about 3%. And so this is the number we want to compare the gauge color code to. OK, so as I said, there's lots of reasons to think about other codes other than the toric code. There are, right? So a very interesting class of models are those known as the color code models. So this is the work of, this is pretty much the career of Hector Bombin. So in 2006 and 2007, with his PhD supervisor, Martin Delgado, he came up with the 2D color code and the 3D color code. So the 2D color code is interesting. It's got physics. It's a code very much like the toric code, except you can perform transversely the Clifford gate set. So when I say transversal, I mean I want to perform some rotation on the code space. What do I have to do to all the physical qubits to get there? Well, a transversal gate means I take every single qubit and I perform some local rotation on each qubit. And performing all these local rotations on each of the qubits will perform the appropriate rotation of the code qubit. And why do we want to do it this way? Well, it's because errors can't propagate this way. So if, in principle, I mean, we all know maths. And so we understand, I have this state and I have this state. I want to map, there exists a unitary that will take this state to here. But what kind of circuit will do this, and what effect will errors have when I go through this circuit? Well, if this circuit involves lots of 2-qubit entangling gates, errors can propagate through the circuit, and like this unitary operation, by the end of it, will have amplified very small errors on the original code, and yeah, we won't be able to recover information on the other side anymore. If it's transversal, there's no entangling operations, or well, 2-qubit transversal gates have a few, but not in a way that's bad. So if we transversely perform gates, perform logical operations, errors can't propagate. So errors that were there, they'll still be there, but they won't have moved or gotten bigger. So this is what we're interested in. OK, so then a little bit later, the 3D color code arrived. And the 3D color code can perform a T gate or a pion-8 gate. And that's interesting because a pion-8 gate, together with the Clifford group, will give us a universal gate set. So that's kind of nice. But the trouble with the 3D color code as a stabilizer code is it has very high weight measurements. So when we start thinking about gate error models, we're not going to reasonably measure the stabilizers very well. So the stabilizers have weight maybe 24. The lattice I'm going to talk about has stabilizers of weight 32 in it. OK, but then more recently, in the gauge color code. So the gauge color code isn't a stabilizer code anymore. It's what we call a subsystem code. And this is really great because we don't have to measure all the stabilizers anymore. We can reduce the weight. We can measure other terms to infer the values of stabilizer operations. The gauge color code, so we've reduced the weights of measurements, and measurement errors become far less problematic when we finally move to the gate error model.
It has it as a feature
feature, but you could see it also as a bug, right? If there's an error in those syndrome bits, then the syndrome seems to be worthless, right? Or even detrimental if you consider it in the error correction.
Yeah, no, it is a bug, but what we want to do is detect those measurement errors and deal with them. Yeah, we want to see where those bugs are. Yeah. So moreover, the gauge color code can also do gauge fixing, which was originally introduced by Patznick and Rijkaard as a way you effectively use error correction to map between. OK, I've gone too fast again. So no code can perform a universal gate set. But what we can do is, right, so that makes the prospects of quantum computation look very bleak. And, well, so the solutions are magic state distillation, and this is circumventing the Easton-Nil theorem because we noisily prepared pionic gates. Or what we can do is what Patznick and Rijkaard propose is effectively having two codes, and we can map information from one code to the other via some error correction procedure. And we can make this mapping without making the logically encoded information vulnerable. And if we choose these two codes smartly, we can, like code A can have some subset of gates, and code B can have the other gates that we need to make a universal gate set. And we can just keep hopping the logical information to each code as and when we need to perform whichever gate. And this circumvents the Easton-Nil theorem because we don't use one code anymore. We have two codes, and together they can form a universal gate set. So the gauge color code can do this, and that's really great. And what's more, single-shot error correction makes it really easy too. Right, so that's what I'm going to talk about. Not the gauge fixing part of this code, but I'm going to talk about using single-shot error correction to error correct for the gauge color code and the advantages this might have. OK, so this is what the gauge color code looks like. So we talk about it sometimes in the dual picture, and the dual picture is very convenient to see the boundaries of the model. So it doesn't actually need to be on a 3D 3 torus. We can put it on a ball and make the boundaries correct, and this will still encode a logical qubit. I'm not going to talk about it on the dual picture, although it is important to see it. There's the ball that encodes a fairly small color code. I'm mostly going to talk about the primal picture. So the primal picture, the code is defined on a 3-dimensional lattice where qubits live on the vertices of the lattice. And the lattice has to be 4-valent, so every vertex has 4 edges incident to it. And also the lattice has to be what we call full-colorable. So these 3-dimensional objects, which I'm going to call cells, I should be able to give them one of 4 colors. And I should be able to assign all the cells a color such that no cell of a given color will touch another cell of its own color. So the lattice that I'm going to simulate, this is an example of a full-colorable lattice, right? You look as hard as you want. You won't see one cell of a given color touching another cell of its own color.
But you said every vertex has 4 edges.
Yeah.
3 edges.
Well, I might not have drawn all the edges on. This is just a piece of the lattice. So it has 4 vertices, 4 edges, 4-valent.
Okay.
So this vertex has 1, 2, 3, 4 edges.
Is it pointing in or out, depending on where you stop drawing? Okay.
Yeah.
Never mind. Okay.
There will be places where you can see 3 because it's only a little piece of the lattice. But yeah, the lattice has to be 4-valent. OK. Right, and so the stabilizers of the gauge color code. OK, so I'm still going to talk about this as a stabilizer code for now, and then I'll tell you what a subsystem code is shortly. So the stabilizers are associated to the cells of the lattice. So you pick a cell. So here's a picture of a cell. And every qubit that touches this cell has a tensor product of Pauli x's. Well, there's a Pauli x. We have the tensor product of Pauli x's on all the qubits that touch that cell. And that's a stabilizer. And similarly, we have Z-type stabilizers. And there is the tensor product of Pauli z's on all the qubits that touch that cell. So take a cell. Pauli x's tensor product is on all of them. That's a stabilizer. Same over here. And we have one of those for every single cell. All these stabilizers commute. It's a stabilizer code. OK. Right, so how do errors look? Well, here's a string of Pauli X errors. And these are going to be picked up by the Pauli, the SZ type stabilizers on the cells. Right, so the 2 stabilizers that will give me -1 outcomes are these bright blue stabilizers that live at the ends, the endpoints of this string. So just like the toric code, we can regard errors as being strings of Pauli operators. Okay, so I'm going to quite a lot now just draw my errors as looking like lines and my syndromes as looking like -1 endpoints of these lines. Okay. Then, right, so this model is a lot like a three-dimensional version of the toric code. So you had Alex Kubitsa visiting, and he's done a lot of work on this. Or interning, I guess I should say. So it's a lot like the toric code, except we have many different colored versions of it. There are 3 different copies of the toric code here, and there's a different copy associated to the different colors of the stabilizers. And the different copies talk to each other in a slightly obscure way. But we don't need to worry about that too much. The point is, this model is a lot like the toric code in 3 dimensions. Okay, right, so how do we deal with these errors? So I'm going to talk you through the decoding algorithm I use. And just so you know, it's the decoding algorithm we use to get a threshold for the gauge color code. It's the first decoder you would have thought to use. So this is Bravi-Haar decoding. Okay, so here's a picture in 3D. And you can think of this as being some lattice of some topological. You've imagined the decoder. You can imagine the next 4 slides, so drift off if you wish. So now, okay, so these red points are qubits that have suffered errors. And close to those errors, we'll see a bunch of syndromes that light up. So they're the black points of this picture. So what I'm going to do is clustering. So what I'm going to do, we can't see the errors. They're invisible. But we use the syndromes to try and estimate where those errors could have been. So the way we're going to make that estimate is we're going to put all the syndromes in boxes. So here are little green boxes. And we're going to incrementally make these boxes bigger and bigger and bigger by finding nearby syndromes. So I make them bigger by, say, 1 spatial unit. And so these syndromes found one another, and these syndromes found one another, and these syndromes found one another. These 2 didn't, because they're far away from everything else. So some of these boxes are turned blue. That's because at the end of each incremental box growing stage, we look at the contents of the box and say, can we explain all of these syndromes with a correction operator that's contained inside the box? And in these 2 cases, we could. And over here, we couldn't, because this box needed these 2 syndromes before we could have explained this with a correction operator inside the box. So we run the algorithm an increment larger, and these syndromes will finally find these 2 guys. And now all the boxes are complete. Every box contains a collection of syndromes, which I should have been calling defects. OK, syndromes, defects. I'll use this analogously. And right, so now all these boxes are blue. We can calculate a correction operator. And the point is, because these are topological codes, and these boxes are small compared to the whole site, that in none of these boxes can I put a correction that will look like some non-contractible cycle around well, I guess this would be a 3 torus. It's not going to span the whole lattice, though, right? So the correction is going to be topologically trivial compared to the logical, the code space or the ground space of this topological code. And so what's contained inside these boxes is a correction operator that will successfully recover the logical information.
This is a 3 torus, so this box is not time. This is all spatial.
This is all spatial.
Fine.
This is all spatial. Right, and so you can see the physical, the red errors live inside these boxes. So this will work out fine. OK. So as I said before, the gauge color code is a subsystem code, not a stabilizer code. So this is a little bit more complicated. And so here's the abstract picture of what a subsystem code is. Don't worry, we don't need all of this level of abstraction, but I'll give it to you anyway. So a subsystem code is specified by what's called a gauge group. So this is a subgroup of the Pauli group again, only this time it doesn't have to commute. But the gauge group allows us to specify a stabilizer group. So if we look at all all of the elements that commute with the gauge group, the centralizer of the gauge group, and we look for the members that commute with the gauge group that are themselves members of the gauge group. Sorry, I think I said that wrong. If it's a member of the gauge group and it commutes with all members of the gauge group, then that's a stabilizer.
It's the center.
The center. Yeah, it's the center. I was corrected the other way once before, but OK. Yeah, OK, I mean the center then. So the center, right, so the center of the gauge group specifies a stabilizer code. There's a distinction between stabilizers and logical operate. That should be an L, I'm sorry. So the stabilizers commute with the gauge group, but are themselves members of the gauge group. Logical operators, not stabilizers, look like they commute with the gauge group, but are not themselves members of the gauge group. And this will specify my whole stabilizer code. Okay, so let's look at the example of the gauge color code. So the gauge group of the gauge color code is, they live on the faces of this lattice. So for every single face of every single cell, we have the tensor product of Pauli x's that touch the vertices of a given face, and also the tensor product of Pauli z's on all the qubits that touch a given face. And we have one face for every single stabilizer. One face for every single two operators. We have an X-type and a Z-type face operator for every single face. Okay. Okay, but it's important to see that these face operators don't all commute with one another. So you can see, let's look at this face here. You can see this will share, so the Z-type face will only share one qubit with this X-type face. So you can see that this face will not commute with this Z face will not commute with this X face. So this is a gauge group. But all the faces, all of the cell operators will commute with the faces. So the way this 4-valent, 4-colorable lattice is constructed means that no face shares an odd number of qubits with a cell. So the stabilizers that I gave you earlier, they're the center of this gauge group. Moreover, we can measure the face operators and learn the stabilizer operators. So this is the next important thing. So, okay, so where I'm going with this is we don't have to measure face operators over and over and over again to learn, to try and identify measurement errors. Actually, we can just measure all the faces once, and we have enough information to learn all of the measurement errors and then all the physical errors, provided the error rate is small enough.
I'm trying to get my head around this. So the stabilizer is non-commutative, right? Because
Stabilizers commute. Gauge terms don't commute.
or the gauge term, the
That's right.
gauge group is
The
not
gauge group
commutative.
doesn't commute.
But there's the center inside, which is the subgroup of the gauge group.
Yeah.
Can I identify the elements of that center
Yeah.
in that graph somehow? If so-
Yeah. So the center are the stabilizers I told you already, the cell operators, right?
Or they're all the cell operators?
They're all the cell operators. So the stabilizers haven't changed. I've just introduced the gauge group. The stabilizer groups are included in this gauge group. Okay. So what's really cool is I don't need to measure the stabilizers anymore. So I can measure face operators, take the product of subsets of face operators, and infer the values of stabilizers. So here's a picture of a cell. And the faces of this cell are 3-colorable, by which I mean the faces, you can assign one of 3 colors, and it won't touch another face of its own color. What's more, every single qubit of this cell touches one color of face once and only once. So that means I could take all the green faces of this cell, say, take the product of all the face operators, and what I learn is the stabilizer operator, the cell operator. So I could measure all the green face operators, and I learn the value of this stabilizer. So if I measure all the faces of this lattice, I redundantly learn this stabilizer operator 3 times. Once through the green subset of stabilizers, once through the blue subset, face operators. Once through the green subset of face operators, once through the blue subset, and once through the red subset of face operators. That's going to let me infer measurement errors in a minute. And that's true of all the cells of this lattice. So that's kind of a neat observation of Hector. Right, and what's more, I'm only going to measure these faces once, and that's going to be enough. And that's going to be very useful, and that's what single-shot error correction is. Okay, so why is this the case? Why does single-shot error correction work? So here's a picture of some cells of the lattice. Okay. Now let's suppose some errors occurred. I haven't shown you the error on the picture, but let's suppose this cell operator was supposed to tell me -1, and all the others were supposed to tell me +1. The big red one in the middle, that's indicating the endpoint of a string of errors. So what that means, okay, and in this diagram, transparent faces give me +1 outcomes, and colored faces give me -1 outcomes. So, okay, so what that means is there's got to be at least one of every subset of the different colored faces that has to be -1. So here's one in the blue subset, here's one in the yellow subset, and here's one in the green subset. Okay, that's nice. But because that had to be -1, if you then look at the cells next to it, so let's look at this guy, this one had to be +1. So this means there's another cell that has to compensate. This cell is -1, and the product of all the blue cells have to be +1. So that means there has to be at least another -1 cell to make the product of all the face operators +1, or all the blue face operators +1. So that means this face had to be -1. And then, okay, so did this cell. This cell had to be +1 over all the blue faces. So this guy had to be -1 to make sure the product of this face and this face became +1 again. So what we see happening is this big string of -1 face operators like emanating from a syndrome. So here's a diagram now, okay? Don't worry too much about the coloring. Here's the -1 stabilizer that is this guy in this diagram. What we see coming from this -1 syndrome is a whole string of -1 face operators. And we have one of these for every single colored subset coming from that cell. So what it means is, if we look at the face operators, not just the stabilizer operators, we have a lot more information to determine measurement errors. So I'm going to show you a picture of that now. So here's, if we just looked at the stabilizers, this is the information we would have seen. We would have seen a bunch of -1 points, and measurement errors occur. We might not have seen all of these correctly. But if we look at all these strings coming from these endpoints, we have this whole spaghetti of information. And we know that these strings don't terminate except in triplets, the way I showed you in the last slide. So what we expect to see, if we measure all the face terms, is some huge spaghetti of data that we can use to identify measurement outcomes. OK, so now let's suppose we measure these face measurements, and errors start occurring. So what does that look like? Well, here's a picture of an invalid configuration, right? So if we look at these green cells, well, these aren't valid because on the blue subset of faces, we have a -1 face term. But on all the other two subset of faces, they both show up as being +1. So this isn't consistent with a physical error. So what we see is broken endpoints of these. I'm calling it spaghetti. I should think of a smarter name than spaghetti, but stick with it. OK, and we see endpoints of these pieces of spaghetti. So these have to be measurement errors, right? That's the only way we can explain this. Right, so instead, if we know to expect some some gauge configuration that looks like this, and we start seeing breaks in this configuration, we can use these endpoints to actually identify the positions of measurement errors. So we take this data, the endpoints of these pieces of spaghetti, and we run it through a decoder again. So again, so these endpoints, they form kind of particle statistics in the same way as the string errors did in the Tourette code. So this clustering algorithm works perfectly fine. That's what we do. And so we cluster up all the endpoints of these strings. We try and estimate what went wrong and figure out what syndrome should have been there. And once we do this, we can run it through. We can reconstruct what we think the perfect syndrome would have been, assuming the measurements were exactly right. And we run the perfect measurement decoder, and this works. OK, so
if you run the decoder on just the endpoints, don't you lose the information which one was connected?
No. So the spaghetti configurations, they're arbitrary. Like, you can't get anything from this. In general, it's a really huge mess. But we do know, yeah, the only thing we are able to identify is the endpoints, and that is useful information.
Get triplets or not. And if the triplets, it's probably good, and if it's not triplets, you've got measurement errors.
Exactly. And right, so we can run this through a clustering decoder. OK, so here we go. I want to figure out how good this really simple algorithm is at working, and I'm going to do this through Monte Carlo simulations. So we prepare a code state. We flip the errors with probability. We flip the bits. We give them bit flip errors with probability p. And then we try and measure the face term. We try and infer the stabilizers by measuring faces, and measurement errors on these face terms flip with probability q is equal to p. And finally, we read out the state. So when we read out the state, this is a little more complicated. We're allowed to measure onto a product state. We're collapsing the code to learn the logical information. So if we measure single qubit Pauli z's everywhere, these single qubit Pauli z's commute with all the z face terms and the z logical operator. I didn't show you a picture of the logical operator, but it does. And effectively, when we measure, this is the same as so if measurement errors occur when we perform this collapse, they just look like physical errors. So effectively, when we read out, we assume a little bit of extra noise, so we add a bit more bit flip noise to all the qubits. And then we make the measurement where there's no measurement error anymore. So this is what happens during readout. OK, so yeah, effectively, here are the maps. We want to figure out the probability of a code of a given size where measurements happen, physical errors happen with probability p. Measurement errors happen with probability q is equal to p. Right, so we run the code state through this map. The physical error, followed by the measurement, followed by the readout, recovers the initially encoded state. I want to figure out how many times out of 10,000 this will occur. And we get a threshold. This isn't interesting yet. I would talk about this crossing point, but I'll tell you why I don't care about this one just yet. So here we have logical failure rate, physical error rate, and 3 system sizes. So the system sizes we look at, I believe a lattice 35 by 35 by 35 is the largest, and 23 by 23 by 23 is the smallest. OK, but this isn't interesting yet, because maybe, here's the problem. I want to run this for a really long time. So that will mean me decoding my gauge color code many, many, many times. And here's the thing. The noise that's left behind after I ran the decoder isn't going to be the same as the noise I put on initially. And I want to give you an example of why I expect this. So here's a string. Here's an error string. And here are 2 syndromes that lit up at the end of the error string. So we have -1 outcomes here and here. Oh, that's what we should have got if the measurements were perfect. OK. But let's say I measure all the phase terms, and this is what I saw. So the original error is shown in gray. I can't see it. This guy, the left syndrome, -1, that was measured just fine. But then we have this spaghetti of information, and we have 3 endpoints that don't truly identify this syndrome. So I have to run it through the estimation algorithm to try and estimate the syndrome. And let's suppose it makes a small mistake. Let's suppose my decoder predicted the syndrome to be here, not in its true position. So we have an estimated position and a true position. So what I'm then going to do is I'm going to put this syndrome into the perfect decoder, the decoder that tries to identify what bit flips have occurred. And it's going to come up with a correction that looks like this. It's going to connect the true syndrome on the left to the estimated syndrome on the right. So the noise that's effectively introduced to the code will look like the initial error times by the correction I applied. And you can deform this onto a small error that connects the true syndrome position to the estimated syndrome position. So different other noise is introduced just by mistakes that are made when I make this estimation. And the error that is introduced corresponds to the discrepancy in position between the true positions and the estimated positions. And so this is a very complicated function. Like, I don't know what this noise looks like at all. I mean, I do. It looks a bit like this. But the extent to which it occurs is difficult to see. It's a complicated function of physical error rate, measurement error rate, and the algorithm I chose to make this syndrome estimation. And so the length of this string I have no idea about, and correlated errors can occur. Long strings of errors can occur depending on how good or bad my estimation algorithm was. And yeah, I don't want to assume that the noise that my syndrome estimation algorithm left behind was necessarily ideal IID noise. So to test this out, what I want to do is I'm going to run my syndrome estimation many times. So I'm going to hit it with some physical noise, and then I'm going to recover it. And then I'm going to do it again and again and again and again. And what I'm hoping will happen is, if I run this many times, I will still be able to decode the extra noise that's left behind on the code. And so I'm going to do this n times, and then I'm going to read out. And I'm going to ask how many times does that give me the initially encoded state. This is now the simulation. And OK, here's what we see. So n equals 0. This is what happens if I didn't run the syndrome estimation at all. I just encoded the information and read it straight out. So this is effectively the perfect measurement decoder threshold. This is the threshold I showed you in the earlier threshold plot. And then I run the threshold algorithm as a function of n. So here's threshold as a function of how many times I run this guy. And what we see is convergence. The threshold after n is about 4 hits this line. And we see a threshold. We call this the sustainable error rate. So even though we appear below threshold, if I were to look at n equals 1 and n equals 2, if I ran for longer, I'm not going to remain below threshold. So this is actually the relevant threshold data to collect. But what we see is the algorithm we ran the noise does equilibrate to something that can always be decoded, or this is numerical evidence that suggests that this is the case, up to n equals 8.
This is for fixed lattice size, obviously.
How does that scale?
Oh, no, these are thresholds. These are thresholds. So
Sizes.
yeah, so each of these plots is calculated using 3 different system sizes.
Okay.
So I'm showing you the crossing point after various n, and this is what we see. Yeah, and well, this is our result, and we find a value of about 0.31%, which is about 1/10 of what we get with the toric code. Okay, what?
Number of qubits.
Well, it's a threshold value, so I mean, I'm only talking about thermodynamic properties at the moment. Overheads are something that I'll talk about that in a minute. Okay, but here's the thing. Although there's a bunch of reasons why this isn't a fair comparison just yet. So first of all, the toric code is received way over a decade of study by now. This is received 3 months of what me and Naomi did over the Christmas holiday. Like, okay, using the simplest decoder we could have thought of. We don't know what the optimal value is. Okay, so we could find much better decoders. Moreover, like also maybe it's worth just, even if this is the best threshold, it's not the best threshold, but even if this is the best threshold, it might even be worth taking the hit because we don't need to do magic state distillation. We can just do this gauge fixing trick. What's more, the fact that we can do this single shot error correcting trick means we can do gauge fixing very, very fast. That's really nice. And okay, there are other benefits of single shot error correction that you have to think quite hard about. Okay, so imagine now I want to build a big quantum circuit. Every time, if there's noise on the quantum circuit, and there is noise on the logical qubits of the quantum circuit, every time I perform a T-gate, that modifies the Pauli noise in a non-trivial way. So every time I perform a T-gate, or every small number of T-gates, I need to error correct it, just to get rid of that new noise I've introduced by adding a T-gate. If the error correction procedure requires that of the toric code where I need to measure for L rounds, this is going to be quite slow. But here with the gauge color code, I can do this in constant time. So there's this polynomial overhead that is just killed for every single gate I want to kill. So every single gate I want to execute. So what this means is, if I take the full length of the circuit and account for the error correction you have to perform at the end of every single logical gate I need to perform, well, I've just shrunk the depth of this circuit by some overhead that I don't need to perform nearly as many syndrome measurements to correct this code. So if I shrink the depth of the code, well, the logical qubits don't need to last as long anymore. So that means I don't need the logical qubits to have such high distance anymore. So being able to do this, single shot error correction is going to reduce the physical overheads of, so there's a lot of benefits that you have to think a little bit about with, yeah, this is one that Hector pointed out. I'm saying this single shot error correction also gives us slightly better thresholds. So even though we have this complicated 3D code, by not having to go to 3+1 space to decode it, we can just do it all in this nice 3D space. Somehow the thresholds remain comparable to the toric code, even though the code is much more complicated. It's 3-dimensional. It's going to percolate, errors will percolate much more quickly, and still we have reasonable thresholds. So yeah, this is, yeah, although the threshold is a bit lower, it's still worth thinking about these codes. They're 3-dimensional, that's a bit disappointing. That's okay, I mean, if we take, maybe we could build these with some distributed architecture. So I talked earlier, and you know, if we have a bunch of qubits spread out everywhere, and we connect them via fiber optics, well, fiber optics don't really care whether or not the code is 3-dimensional or n-dimensional, right? So there are ways we could build this quite easily, I guess, or as easily as any other code. Okay, so where do we go from here? So I've argued that this code is certainly worth studying. I'm not saying it's better than the toric code, but it might be. And our results are in this direction, provide evidence that support this. Right, so what we need to do is we need to study the model with more realistic noise. As I say, we worked with phenomenological noise, and to compare it truly with the toric code, we have to take these 6 body measurements into account, whereas the toric code only has 4 body measurements, and this will cause the threshold to suffer a little. Yeah, so we need better decoding algorithms. We have them, we know what they are. It's just a case of sitting down and writing the code and getting some student to do that. Okay, we want to compare, yeah, so this was, as you were saying, we do need to compare the overhead, so we need to be in some regime where P is quite small, like way below threshold, and then ask actually how many physical qubits do we need to run this circuit? And it's a very complicated question for the reasons I was explaining, like the fact that we can shrink this circuit depth using single-shot error correction, that's awesome. But it's a 3D code, so you lose some qubits again because the distance scales less well. Okay, and the questions I'm really interested in is what is single-shot error correction? Like, we have examples of it. We know it's related to self-correction. So the gauge color code is an example of a code that performs single-shot error correction. So is the 4D toric code that I talked about. But I'd be keen to see that it's impossible somewhere. I think I can nearly show that the toric code definitely can't support single-shot error correction. That sounds like a trivial statement, but there are technical details. Yeah, I would like to see that single-shot error correction. Yeah, I want to know what fundamentally promises single-shot error correction, and then we can, in principle, find the simplest code that can implement this, and this could be very useful for reducing overheads of quantum architectures. And with that, I'm done. I didn't put a thank you slide in, but thanks for your attention.
Great. Well, thanks a lot. We had a lot of great questions during this. We got 5 minutes left. I'd like to open the floor to questions.
So your error model, I forget, were you pretty much just considering bit flip errors?
Mm-hmm. That's right.
Right, so maybe just a question, maybe slash comment. I mean, I know this is sort of, you're kind of just getting started in this direction, but bit flip errors kind of, you have some preferred direction that is flipping, but you have now 3 dimensions, right? So do you expect that realistic error models will be bit flips, or like, so depolarizing errors would be more well, they're not going to favor any particular direction. Have you considered depolarizing noise?
Yeah, I mean, we can deal with this, right? I mean, we have, as I said, I wasn't explicit about this in my talk, and I realized somewhere towards the end that I wasn't. But we have Pauli X and Pauli Z stabilizers, right? So the way we will deal with this is, if we were to study depolarizing noise, is we'll measure all the X-type stabilizers, well, the X-type phase operators, learn the X phases to deal with all the Z-type errors. We will regard Y errors as X times Z errors, so we'll correct for those at that point. Well, the Z part of those errors at that point. Right, and then we'll measure the other flavor, I can't remember if I said Z or X, but if we measure the X's first, and then the X stabilizers first, and then the Z stabilizers second, and then we just repeat and repeat and repeat. Maybe if you're really smart, this is something nobody's even thought to try with the 2D color code, actually, but you could, in principle, measure X faces, Z faces, and Y faces, and you kind of symmetrize over all the bit flip and phase flip errors. Yeah, okay, if you have more knowledge of your noise model, so maybe dephasing occurs much more rapidly than bit flip errors, then maybe you'd measure bit flip errors, phase flip errors a few times, and then deal with the bit flips a bit later on, and make it a bit anisotropic. Yeah, I mean, yeah, we know how to deal with this.
Have you done any simulations yet along that route, or that's future work?
That's a headache. Yeah. No, I haven't simulated that. Bit flips are interesting. I would rather write a better decoder before going on to other types of noise. I mean, this is, in principle, shows that I can deal with all the types of noise that you're proposing. Yeah.
Any other questions? Well, if not, let's thank our speaker.